So some of you may have already been trying to answer question 3, and in part C, it talks about the equilibrium and the stability properties. And I guess some of you are panicking that you don't know how to do this, but you're going to learn today. So if you've come across this and you've been worried, then we'll cover it in class today. Are there any questions about the material so far, or the homework assignment other than this third part? Okay. Yeah? Well, we can ask the GSIs, but when they go through it, it should be self-evident that from what you put down, that everything follows. So we don't want to see long explanations. We don't want essays. But, don't just put stuff down that somebody say, where did that come from? So try to be, explain. So the grading's a little more lenient to begin with, and then we'll tighten up as the course progresses and you learn what's needed. Okay, so we're going to continue talking about difference equations. And in the textbook, we talk about sequences an plus 1 is a function of an, whereas in this class, we usually focus on the notation xn plus 1 is equal to fxn, because when you build models, it's more usual to use a variable x. But in math texts, calculus books, if you have a look, they very often use the letter a for a sequence value. But now what this says is that as n progresses over time, so for example, you can simulate this model if you said that f of x or f of a was this function an plus r an 1 minus an over k. And this is sometimes called the logistic. And you should pay attention that in this class and in the textbooks you'll see two versions of the logistic. You'll see this one. This is not a very good color. Doesn't show up. I'll try using black. Can everybody read this, even though the light's not on? Okay. So xn plus 1 is equal to xn plus r times xn, 1 minus xn upon k. That's one version of the logistic equation that you'll see. Another one is xn plus 1 is equal to r times xn over 1 minus xn over k. In the first case, f of x is equal to x plus rx minus rx squared. This is the first case. So in case 1, these are really terrible. And in case 2, f of x is equal to r times x minus rx squared upon k. And I'm also going to divide through here by k. Sorry, just the x squared term. So you'll see that this has an extra term x. So it behaves a little differently. And if you build this model and this model, they do very similar things, but for slightly different values of r. So don't be confused. These are two different models. This is sometimes called the logistic growth model, and this is sometimes called the logistic map. But you'll see both, so don't be confused. Okay, so if we have one of these, let's say the logistic growth model, this one up over here, and we give k the value 1 and r the value 0.3, we can simulate starting out, say, at x equals the first value 0.1, and you'll see the population grows, but it's approaching a constant value. So this idea is that it has a limit. So you can say if the limit of an, as time goes on, approaches a particular value, and in this case, the value would be 1. And it doesn't matter whether we start above 1 or start below 1. If we start below 1, the sequence grows towards 1. If we start above 1, the sequence drops towards 1. If a limit exists, we call it an equilibrium. And at the equilibrium, we get the condition that x equals f of x. So in the case of 1, the equilibrium is the solution to the equation x equals x plus rx minus rx squared. And we're doing this for the case k equal to 1. So if we set k equal to 1, then the equilibrium is going to satisfy this equation. And if we solve this equation, then we can subtract x from both sides, and we have rx, and we can say rx into 1 minus x. So we subtract x on both sides, and then we take out a common factor rx is equal to 0, which means either x is equal to 0 or x is equal to 1. So that's the equilibrium for that case. The equilibrium for the other case, for 2, we would solve, the equilibrium equation would be x equals rx minus rx squared. And so if you solve this, you can say this is the same as, if we take rx to this side, it's going to be x into 1 minus r minus rx squared, or we take this over, is equal to 0. And then you can solve that for x and r. And one solution is x equals 0, and the other solution is rx equals 1 minus r, so that x equals 1 minus r upon r. Okay? Does everybody follow that? Yeah. X equals f of x. But yeah, x equals y. So that's a good observation, because if we come to our plot here, and our model, if this is x, and this is f of x, and so you're calling this y if you want. In our model, for example, that might be f of x, and this might be, so this is y equals f of x, and this is y equals x. And the equilibrium occurs when f of x equals x, so it occurs there and it occurs there. Because f of x equals x, where these two curves intersect. So that's true, yeah, okay? Okay, so, no, I said it, I just chose k equal 1. Yeah. In fact, the reason for it is that if I don't choose k equal to 1, it actually cancels out because the equilibrium value is k rather than 1. In all this analysis, k is just a scaling constant. And the way you can see it is that if I replaced x upon k by something called z, then you could show that you can replace everything and you get an equation in z that didn't involve k. I'm not going to do that. But it just turns out that k scales this axis. And that everything we say about the behavior of this equation, that's actually only for the logistic map. But anyway, sometimes I set a parameter equal to a particular value just to see what happens. I just set it equal to 1. But as I said, it turns out that R is much more important for affecting the behavior of this process than K is. And when you do your, when you simulate this model, if you choose a larger value of R, so if we choose K equal to 1, but if we choose R equal to something like, in this case, 1.9 or 2.2, you'll see that when R is equal to 2.2, you don't get an equilibrium. What happens is the model goes up and down like this, so you don't get an equilibrium. That doesn't mean an equilibrium doesn't exist. But because if you solve the equation, x equals f of x, you still get the same equilibrium. But you don't approach it. The sequence doesn't approach it. So this particular theorem over here just says that if the sequence does approach it, then it's an equilibrium. If the sequence doesn't approach a limit, then it doesn't mean you don't have an equilibrium. But what we're going to find out is that we call that equilibrium unstable. And we're going to see in what sense it might be unstable. And if we come back to the logistic equation, and again, in your homework assignments, we can either choose, for example, we can choose k equal to 100. So that just scales this axis so that the equilibrium is at 100 instead of 1. Some people like to work with integers rather than with decimals, so then it's convenient. If R is equal to 1.5, you'll see that the simulation or the sequence approaches an equilibrium depending where you start out from. So here we start out at 99, and then we go to 100.4, and then 99.8, and then 100.2, and eventually we approach 100. Now here you can see that if you choose R equal to 3, we get this chaotic behavior. So we don't even get a cyclic pattern like we saw over here. Here you see that the behavior is periodic, so we call that a 2-cycle. So why does this happen? And our cobweb diagrams can help us understand this. So I'm going to switch the light on. So let's consider the model f of x is equal to R. And let's draw this model. And what I'm going to do now, which I haven't done before, is I'm going to allow for x to have negative values. It doesn't make sense in our population models, but sometimes x can represent a quantity, which is how much above or below a particular level are we. And if we're below the level, then x can be negative if we're above the level. So some models can be a model about how close are we to some particular level. And so you can get negative values that are meaningful in the sense that they can say, well, we're below that level. And then we put in the 45-degree line, y equals x. And now, if R is less than 1, then this is what f of x looks like. F of x equals R times x. And this case is R is less than 1. Now, if we start out at some value, and the way we calculate the sequence is we start out at this value, we go to the function f of x to calculate the next value, we go to the 45-degree line to project down to the value where we go to next, to bring us to the next value. And then we project down to the 45, from the 45-degree line to get our next value of x. So if this is x0, then this would be x1, and this would be x2. And so the cobweb says just continue like this. And you see that we're stepping towards 0. So because we're stepping towards 0, that's the limit of the sequence, that's an equilibrium, and we say it's stable. Okay, let's see what happens now if f of x has slope greater than 1. Okay, so let's draw f of x. This is y equals r times x, where r is greater than 1. So it lies above the dotted line. Now let's start off at a particular point. And if f of x is equal to rx, then the equilibrium, x equals rx, to find the equilibrium, this has a solution either if x equals 0 or if r is equal to 1. But for other values of r, the only solution is x equal to 0. So the only equilibrium is x equal to 0. So now let's see if we'll go towards the equilibrium. So we start out at some value. We go to the function. Then we go to the 45-degree line. Then we go to the function, the 45-degree line. And so if we start out here at x0, then here we have x1, x2, and we see the solution is growing. No matter how close we start to the equilibrium, we grow away from it. Okay, so that's the linear model. Now, if, for example, it made sense, to have a model where the function could be negative, and as I said, there will be situations where that does make sense, then what is going to happen? Well, now, if r is going to be negative, it has to have negative slope, so we have to go through, to get negative slope, we have to go from this quadrant to this quadrant. So if we start out like this, then we can apply the cobwebbing, and so We start at a particular value, we go to the function, then we go to the 45-degree line, then we go to the function, then we go to the 45-degree line, then we go to the function, then we go to the 45-degree line. So what do you notice is happening to the solution now when we do this? We start off here with x0, then the next value we get is a value over here, which is x1, then the next value we get is x2, the next value we get is x3. So what do you notice is happening? What is happening? Yeah? Yeah, so it's approaching 0. Let me just draw what the solution would look like. So here's 0, and we start out at a particular point here, x1, and then we go to a point here, x2, but this distance is closer to the origin than this because this line has a slope between 0 and minus 1. And then we go back to this value and then this value. So the solution is going like this. It's oscillating, with the oscillations getting smaller and smaller and approaching the equilibrium. So we say the equilibrium is stable, but we're getting oscillations. So that's this particular case here. But if we get a slope, f of x, that is negative but is steeper than minus 1. So remember, as this gets steeper, it approaches an infinite slope, but it's always negative. Then instead of winding in to 0, which means that we're jumping on either side as we get closer and closer, what happens is we jump on either side and we get further and further away. So it's unstable. Now, why do I label this point? The point is that whenever you get an equilibrium, you can look at the slope of the curve at that equilibrium. So let's have a look at a couple of cases. So if you remember the Bellows model, and this is the model you're drawing in your homework, we have what's called the generalized Beverton and Holt model. So here we've got f of x against x, and we can put in the 45-degree line. And in some cases, we may get a curve that goes like this. So this is the equilibrium, because this is where x equals f of x. And don't forget that this is also an equilibrium. So here we see the slope of the function at the equilibrium, and the slope of the function we write f dashed, and we'll call the equilibrium x star. In other words, when we set up this equation, x equals f of x, and we solve it, we get a couple of values. We saw that how we did that in the logistic equation. We got x equal to 0 and x equal to k, or x equal to 1 when k was set equal to 0. So we evaluate this at the equilibrium x star. We look at the derivative, and that tells us the slope of this function. So the slope of this function at this equilibrium, you can see that this slope lies between 0 and 1. This slope here, this is another equilibrium. So this is 0 less than f star, f primed at x star, and f primed is the derivative of f. So we use the prime notation is equal to df dx. And then if we put in the argument x star, it means we are evaluating the derivative at x equal to x star. So here we see the slope is somewhere between 0 and 1. And here we see the slope is greater than f, and in this case, x star we know is 0, so we'll just write f primed at 0, is greater than 1. Now if it's greater than 1, locally we know what's going to happen. What's going to happen is we're going to go from a point to the line, to the 45-degree, to the line. So we're going to wind out from, we're going to move away from this point. So this point's unstable. Over here, what will happen is if we start at a particular point, we go from here to the 45-degree, to the line, to the 45, and the same thing. If we start out here, we go from here to the 45. No, that's not working out. Sorry, there, to the 45, to the line, to the 45. So this line, so these points move in towards the equilibrium. These points move away from the origin. So you get these two situations over here. You get this one moving away. Now, here the slope is actually greater than 1, so it's not like this case. And in fact, if you get a more complicated function, like the Beverton and the generalized Beverton-Holt function, which turned over quite strongly, how many of you have plotted the function yet? Okay, you'll see that the function looks like this. I'll draw it in blue. So you'll see that over here,